Which boiler do we use RO water for?
Boiler 4.
Boiler 4. Okay, another question. Why do we use RO water for boiler 4?
Because of the super.
Yeah, basically, okay, so yeah, because of the superheater. That's a really good answer. We often do get a certain amount of carryover, and so if we've got a drum type boiler, maybe we've got, a really good one. If you got the right kind of steam drum internals, maybe you get 99.5% dry and saturated steam entering the superheater. But what about that 0.5%? Or what about that 1% of moisture? Well, it carries impurities with it. And it doesn't take long for impurities to build up on the superheater, and then we get a failing superheater. Um, so that would be no good, right? The only thing that's keeping our superheater cool is the flow of steam. And the heat transfer between the hot flue gas and the steam is not the same as the hot flue gas to boiling water. So it doesn't take long for deposits that occur in the superheater bank, or in a reheater bank for that matter, to cause us some really bad overheating problems. So that's why we use the RO water. So what about this RO system stuff? So, we got the RO. I don't know how much you studied about it. Did you study much about it last year? I will take that as a no. I mean, you know how to run it, you know how to test it, where that water is. So what is osmosis then? Osmosis is, okay, here I've got a solution in a beaker, and there's a membrane. And believe it or not, the solutions have the same solvent and the same solute. The solvent, of course, is water in our case, and the same solute, which is going to be, a combination of, we're going to have some calcium ions in there. We'll have some magnesium ions in the case of hardness constituents. We'll have some sodium ions in there. Maybe we'll have some iron ions, whatever. So we have all these ions, but it's basically the same stuff on each side of the membrane. And what you'll notice is we've got fewer impurities on one side of the membrane than on the other side. So here we've got a concentrated solution. And then over here, we've got a weak solution. And the miraculous thing is this. It's freaky and it's weird, but what's going to happen is the solvent will flow through that membrane. Why? It's called osmotic pressure. I don't know why. It's amazing. But what's going to happen is the solvent will flow from one side to the other until the concentrations are the same. So we start off with a weak solution on one side of the membrane, a concentrated solution on the other side, and now what we'll have is, I don't know, intermediate concentration on both sides, but the same concentration. And so this is observed experimentally, right? I mean, they take two different concentrations, in this semi-permeable membrane, and that membrane has got really super tiny openings, right? So it's basically like a molecular sieve. Molecular sieve, I think is SIEVE, or maybe it's SEIVE. I don't know. It's just that weird English spelling business. So it's a molecular sieve. And so what it does, it permits molecules of particular sizes to go through, and it'll keep larger molecules from passing through. So the solvent can pass through, the solute cannot, and so what we end up with then is this difference in height. And we know that the pressure at the base of a column of liquid is equal to, pardon me, rho GH. Pressure is equal to, let me do that again, rho GH. Well, in other words, we've got a particular height between those two. And if we know that height, we know the force of gravity, we know the density of the solution, we can determine what that pressure is due to the head of a column of liquid. And as a matter of fact, that pressure, we're going to give it a name, and we're going to call it osmotic pressure. Does that make sense? Now, reverse osmosis then would be applying enough pressure on one side to overcome the osmotic pressure and make it work in reverse. That's why we get this term reverse osmosis. So here we've got the osmotic pressure, and we can have it expressed in terms of height, or we can have it expressed in terms of pressure. And if we apply pressure, and so this would be from a pump, basically a high pressure pump. I'm having some problems here. A high pressure pump. We can apply enough pressure to this concentrated fluid, and we can overcome osmotic pressure and force the fluid to go backwards against what it's trying to do naturally, right? The fluid is trying to naturally equalize the concentrations, but in the case of osmosis, we're applying enough pressure to overcome that natural osmotic pressure. So when you think about it, really what we have is a glorified filter. Okay, it's a filter, yes. It filters out tiny little particles, yes. But it actually works against the concepts of osmosis. So that's why they call it the reverse osmosis system. So what we have, after we've applied that force, we've applied enough pressure to overcome osmotic pressure, we get fluid going backwards through the membrane, so the solvent goes through. This stuff here ends up sort of being purified, and that stuff has a name. It's called the, wait, let me think of it. It's called the, anybody know? There's a couple of names here, and they, maybe it's on the next slide. Aha, okay, yes. The permeate. Okay, so that's what we're going to put into the boiler, the permeate. And this stuff here is the concentrate, and basically this is going to go to waste. So two terms you need to know, concentrate and permeate. The concentrate is the bad stuff. It's the stuff we've sort of filtered out, and the permeate is the good stuff. It should have very, very little dissolved solids in it. Now, we don't want that stuff to go directly through the membrane. What is preferable is if we have something called a cross-flow membrane. So what we do is we make the high pressure here, and there's actually a flow that's at a tangent to the membrane. So we're not putting stuff in at right angles to the membrane. We are having the flow parallel, I guess, to the membrane faces. And so this allows us to, okay, let's say that some of these particles kind of end up plugging off the membrane. This flow tends to sweep away those particles so it doesn't plug the membrane. So that is a cross-flow reverse osmosis membrane. So what do we end up doing with this membrane? Removing most organic compounds, like 99% of all ions. We can remove viruses and bacteria. 99.9% of viruses and bacteria. What kind of pressure is required to overcome osmotic pressure? Well, from my source, it said 345 to 6900 kPa. So you can find this online, this Osmotic Pure Water Handbook, second edition. It's free download, PDF. It's a pretty good book. Now, why would we want to use this instead of distillation? It uses less energy. Well, why would we want to use this over demineralization? Well, we don't require all those nasty chemicals, so we don't need sodium hydroxide, we don't need hydrochloric acid for regeneration. We don't have to worry about disposing these strong acids or strong bases used with regeneration. So it's environmentally friendlier. Friendlier. Environmentally friendlier. So there's still the whole idea of the concentrate. You got to dispose of the concentrate. Okay, I mean it's not great stuff for the environment, frankly, but I mean it originated in the environment, so you're kind of putting it back into the environment. There's a fairly big initial cost in a very large RO system. Let's say too that these systems are good for final polishing. So just like the demineralizer, we don't want to take really hard water and whack it through the demineralizer. We're going to use a lot of chemicals. We're going to get a lot of premature fouling of resin. What we want to do is use a demineralizer bank to take water that's already been softened, had the bulk of the hardness removed, and then the the demineralizer and the mixed bed are going to do that final polish. They're going to remove all of the ions and give us ultra pure water. And it's a similar situation with the reverse osmosis. We're going to remove the bulk of the hardness first, the impurities, and because otherwise this stuff would foul the membrane prematurely. So really, we use this for polishing. Now, what you have in the lab on the, is it second floor? Yeah, second floor water treatment room. We've got that RO, and it's this type of thing where we've got these spiral wound membranes. Okay, let me just think about this. So what we get is the water is fed into, so think of this being kind of in a can container, okay? And we've got the feed water goes in between the membrane. It's a cross type of membrane, and then on the inside we've got a pipe, and there's some O-ring seals on it. And so what happens is, due to the high pressure here, this high pressure feed, we overcome the osmotic pressure. We end up forcing the permeate into this perforated pipe that runs the length of it. So the permeate comes through and goes off to the boiler. Actually, it's going to go to the deaerator. It's going to be makeup, but I'm just going to say boiler anyway. And then what comes from this membrane area, but at the other end, is treat. And there you go. That's all I have to say about reverse osmosis. Do you have any questions about RO? Then I move along. Objective 11 is about deaerators, and you know what they are. You know what they do. We're removing dissolved gases with heat. What I will say is that they are ASME code section 8 vessels, and so they have to have a relief valve on it. And there are different types of mechanisms. There's a spray deaerator, tray deaerator, bubbling deaerator. There's even vacuum deaerators. But they also function as feedwater preheaters. So I know that if you have lab with, who would you have that with? Clayton, I guess. And you go over the regenerative feedwater preheating system of Unit 4, the deaerator is considered to be one of those regenerative feedwater heaters. You should know the kinds of fittings that we find and how these things work, and lots of different variations. And you should know the relationship between dissolved oxygen and, for that matter, dissolved CO2 and temperature. And what we see is this inverse solubility curve, where at low temperature we get a certain amount of solubility, and at high temperature we get almost zero solubility of dissolved oxygen. So that's the point of this thing, is to get rid of dissolved oxygen as well as dissolved CO2 and vent that to the atmosphere. How good can we get? 5 to 7 parts per billion. Now, that's still unacceptable, really. What we're going to do is we're going to add some sort of an oxygen scavenger as well, very commonly Na2SO3, which is sodium sulfite. That's sulfite, not sulfate. But when this stuff, when we have 2 of these and we have some dissolved oxygen, then we end up with 2 sodium sulfates. That's where the extra oxygen is going to. Okay, so sulfite becomes sulfate. Please don't confuse sulfite and sulfate, or I'll hate you forever. Now, what have we just covered? Oh, so this is just a really kind of crude overview, but we got a raw water pump here. And maybe it's pumping from a lake or a river, or maybe it's coming from a well. This is going to be our makeup water. And depends what's in it. Maybe if we've got dissolved solids, suspended matter, we're going to have a clarifier settling tank. If we've got dissolved iron, we'll also have an aerator. But either case, what we have is an open vessel. And whenever we have an open vessel, it is followed by a pump to repressurize it, because there's no way that we can get the water from this open vessel through the rest of the system. So we've got a booster pump. Okay, so one of the principles that we follow is that if we've got an open vessel, we need to have a booster pump. Then we have some options too. Do we want to put it through a cold lime soda softener? Do we want to put it through hot lime softener? Do we maybe want to put it through a dealkalizer, followed by a decarbonator? Do we want to put the water through just a sodium zeolite softener? Okay, the main thing is we'll have, usually if we're going to use H2Z or sodium zeolite on its own, then what we would have is a system where the raw water makeup um, might be safe from the city water or municipal water. So, for example, here at SAIT, our raw water is hard, yes, but it's not super duper hard, so we can put it right um, into a sodium zeolite softener. So that softened water goes to boilers 1 and boiler number 2, and I think it goes also up to the 4th floor for the low pressure steam boilers and the high pressure Cleaver Brooks. But then as for unit number 4, we've got a system that's very, very intolerant of dissolved solids. We also don't want alkalinity in there, so what we'll do is take the effluent from the sodium zeolite and we'll put it into an RO system for final polishing. Or maybe what we could do is put it through a cation-anion exchanger if we want to have demineralized water. Or we could put it through a dealkalizer system. It really depends what sort of water quality we're looking for. Ultimately, we will make up to the deaerator, and the deaerator, with the application steam, we're going to vent out our non-condensable gases and to the boiler feed pump. So that's a very, very crude and very limited overview compared to what we've actually looked at. We've looked at a lot more stuff than that.